Can you hear me?
Yes.
Okay, so let's start today's course. My part is entitled as Applied Machine Learning for Chemistry. And we have 2 slots. So from now, we have 90 minutes for first part. And after the lunch break, we have another 90 minutes. And I am Ichigaku Takigawa. And first of all, first thing to ask you to do is please access this website. And you will see some the slide of this presentation, and also the one for the next slot, and as well as some small example of Python code used in this lecture. Okay. So, and first, my name is Ichigaku Takigawa, and I'm from Institute for Chemical Reaction Design and Discovery, Hokkaido University, as well as I belong to the RIKEN AIP Center, which is the research center for machine learning. And basically, I am not a chemist. I'm a computer scientist, and my research topic is something called machine learning. So today's topic is basically some basics of machine learning. In particular, when we try to apply machine learning to your problem, for more specifically, there's some chemical problem. And my background is basically pure computer science, but my career is a kind of interdisciplinary field, such as bioinformatics, chemoinformatics, and chemistry and pharmaceutical sciences, and as well and also materials informatics. And also now I'm working for some biology team in RIKEN. And also I am running some chemistry-related project in Hokkaido University. And this is some brief agenda of today's lecture. And basically, this is a course for chemistry students. So I don't assume anything about machine learning or computer science. So I will try to explain a very essential concept of machine learning and some careful points you should take care when you apply machine learning to your problem. And also, I want to encourage you to actually do or run some small machine learning program on your PC or even on your smartphones. And probably most of you have a PC or smartphones, so you can try machine learning in this course or after this course. If you have a web browsers. And next course is more specifically dedicated to machine learning. But basically, I will skip all technical things, some that require some mathematics. And also, I will try to focus on the concept. And basically, so the explanation should be for everyone. So let's get started. And the first topic is, of course, our topic is machine learning. So I will try to explain what machine learning is. And consider janken, so rock, paper, scissors game. And you assume you are asked to write some programming code for rock, paper, scissors robot. If we have any. But the first task we should do would be write some small code for a computer to recognize the hand shapes by a camera or some video camera or something like that. So then we can, so if computer can recognize this hand shape is a rock, then we can come up with some algorithm how to play in janken. But it turns out probably you will instantly recognize this task is really, really hard to handcrafted programming. So probably some some of you from computer chemistry and probably know some sort of programming, like I'm not sure, so C programming languages or Fortran or Python or something like that. But using that programming language, write a code for this task is very difficult because everyone have very little difference in hand shapes and also different skin colors, different, angles, and different lighting environment or something like that. So many variation about this image, the photos are possible. But probably a human can do this task easily. So probably, basically, you will instantly recognize which is a rock, which is a paper, which is scissors. So how to write a code for this task. And machine learning is very good at solving this kind of tasks. And this is some very brief general definition by Tom Mitchell. And machine learning is basically concerned with the question of how to construct a computer program that automatically improves with experience. And this is very abstract explanation, but this task below, the tasks below requires some sort of experience rather than some single predefined principle. For example, you can recognize the spoken words, like what I'm speaking, or you can recognize your or friends' handwritten characters, and recognize faces, so who is who by seeing the face. You will instantly recognize he is or she is who. And you can walk, speak, swim, ski, and that recognize some sort of a practice or at least some experience. So probably if you just read a book to explain how to walk, probably that is not enough to actually walk. So this Janken recognition basically requires some sort of experience. So actually, we need to grasp what kind of variations can happen in this game. So basically, we can use machine learning, and here, machine means a computer program, so we want to build or write a computer programs, and learning means automatically improve with experience. But what exactly these sentences mean? And basically, every computer program processes input to get output. So, for example, if you have some video game hardware, then if you push the button, this is the input, then the screen is rewritten accordingly. Or if you have if you want some money at the convenience store or somewhere, then you put some, I don't know, a secret code or password for your accounting, then you can get money if your password is correct. This is some program inside this machine. And also, if you search the web, then you input some keyword, query keyword, then, for example, the website of Google returns a list of a website which is relevant to your query. And this is also the program. Then actually every program processes some input to get output. But usually this part is we need to explicitly what's happening in these programs. So this is a kind of a standard programming. We manually code a computer programs using computer programming languages like C languages, C++, Python, Fortran, or some whatever. You need to explicitly write a computer programming code accordingly. But program is for those tasks. Actually, we don't know how to do it explicitly. So actually, we can speak languages, but we cannot explain why I or you can speak Japanese, English, or some other languages. So you can do is very different from that. You can perfectly recognize the process. So the machine learning is a very lazy approach to this task. So actually, we basically give up what's happening inside this. But instead, we just are giving some input-output examples. So if this kind of sound wave is inputted in the microphone, then it means hello. And if this wave shapes, this corresponds to machine, and this wave sound shape corresponds to learning, or something like that. So if you input many variations of hello, many variations of machines, or many variations of other sentences, words, then we can, machine learning automatically build these computer programs, which process this input to desirable output. So here, in short, machine learning is a very convenient way to build a computer program directly by given a set of input-output example without being explicitly programmed inside here. So in this sense, the machine learning is kind of a new way of programming, computer programming. So if you this kind of tasks, I will explain, I will list some practical example later. But anyways, if you have some sort of very obscure, unclear process, but you need to implement this computer program for some purpose, then probably machine learning will be the nice option. And the more typical cases, you have some Excel data, so tabular data here. And for example, this is a very typical problem called iris recognition. So iris is the types of flowers, and you can see some roadside or somewhere. And it has mainly 3 types of species. And this program is, if we try to build this program by, or if we classify the iris flowers by these 4 quantities, so variables. So iris flowers have 2 types of part, and petal and sepal. And we have, if measure the length and the width of a petal and the length and the width of a sepal, we have 4 numbers. So problem is, if we input the 4 numbers, then we want which is the target species, the target flower species. So this is solved by machine learning. We will see that later. So the important thing is we need a set of examples. So we need to give many examples to machine learning programs. So even for us, so we can probably, if you are Japanese speakers, you can recognize the difference between this character and this character. But non-Japanese speakers, sometimes it's very difficult to distinguish these 2 characters. So what's the difference is a basic experience. So Japanese speaker is repeatedly see this kind of variation of and variations of me. So we can recognize the characters accordingly, but that does not mean we understand the rule of difference between A and B. It's a empirical rule, so it's obtained from the experience rather than some explicit rule. So angle of this line is, for example, larger than some degree and less than some degree. That kind of explicit rule would not work for this recognition program, because we can, if we rotate R, we can still recognize R. See, so this is our way to get this task solved. So, but what actually means the emerge from the many examples? So statistical rule will be emerged from many examples. So if we consider this problem, this is a factory line to classify apple or orange into the 2 factory lines to, I don't know, ship somewhere, some supermarket or somewhere. Then this sensor observed 2 quantity, weight and height, then we can apply machine learning here. And actually, the statistical rule emerges like that. So if we plot the height at the x-axis and the weight at the y-axis, then if we have some example, we can plot each instances as a point in this 2D plot. So we have a small sample like this one. But if we give many examples, then so situation is gradually, we can see some patterns here. And this is, of course, artificial data, but the point is something like that. So if we see many examples, we can, some rule, so some classification boundary around here. So if the point falls in this region, probably it's an apple. But if it's falling this region, probably it will be orange rather than apple. So this is like this way we can build a fluid sorter if we can get this curve explicitly. So machine learning is basically converts many examples into these some flexible curve or surfaces or boundaries. So this requires some set of examples. So if we have 2 or 3 examples, still we can solve this one, but it's not so statistically reliable. So if we have many examples here, then probably that rule is very useful. So anyway, if more simple cases, then if we input the one real number here, for example, let's say 3.1 or something, then converts some other real numbers, like squared or something. So we want outputs, when we input 3.1, we output 3.1 squared. Then we can solve this types of convert program by machine learning. To solve this task, we need some examples, input-output example, which is called training data, usually. And this is a pair of input and output. So if we have x, for example, we want x squared or something. Then if we have this kind of training data, both inputs and the output is one number here, then we can put training data as a point in this 2D plot. So x-axis input the value of input number, and the outputs will be the desirable output numbers. So if we have a set of training data, we can plot training data here. And here, what machine learning should do is machine learning program needs to return outputs for any arbitrary inputs. So basically, machine learning is a kind of curve fitting here. If we can some sort of a probable outline of probable curves here, then, for example, if we want the outputs for this new input, which is not in the trained data, but we can compute the outputs using this curve. So this is basically very core of machine learning. So, which is one-dimensional. That's the machine learning is basically do this in very high dimensional. So let us add one more dimension. So we have if we input the 2 numbers here, and then output 1 numbers, then training data is a pair of 2 numbers and a desirable 1 number, output of a desirable 1 numbers. So here we need to, rather than fitting the curve, we need to fit the surfaces or like appear here. So if we input the x1 and x2 here, then if we want to make a prediction on this new input here, so x1 value is here and the x2 value here, then input here. Then we can get the output after the fitting these surfaces like this way. So this numbers is prediction of our outputs for this new input. And if we draw a line over the contour plot xy, x1, x2 only, then we can see some sort of boundary plot, like a fluid sorter examples. Fluid sorter cases, that's the two values given, so apple and orange. So just the two color partition over this space. But in general, we can consider the continuous number here. Anyway, this is machine learning in two-dimensional, and also probably most of you can guess actual machine learning is basically do this kind of stuff in very high dimensional. So for example, if we want to build some handwritten character recognized here, the handwritten digit 3, probably 3. And if we observe this handwritten character as, for example, 28 by 28 pixel images, then we have and each pixel have some value between 0 and 1. And if it's very close to black, then it's close to 1. If it's very white, then value will be close to 0. So we have actually 28 by 28 real value array, so which includes 784 real numbers here. Then we want to convert this 784 numbers to 10 real numbers here, and each will represent the probability for this input is being 3 or being 8 somewhere. So this here, machine learning model is a kind of fitting the 10-dimensional valued function in 784 dimensional space. So which is probably sound like a non-trivial task here. But anyway, we can solve this task exactly same way for 2D and 1D if we use machine learning techniques. But anyway, the machine learning is something like that. So build some mapping from the input to output to reproduce the given input-output examples. Okay, so the machine learning, in other words, is basically the high-dimensional interpolation by function or some surface model, curve model fit into the given input-output example. So as you see in the one-dimensional cases, it's just a curve fitting like this one. But basically input can be a very high dimensional, or either output also can be very high dimensional. In the previous case of about 10-dimensional output, if we want some probability. So the machine learning is basically curve fitting in simple words. So can you get the idea here? So, but basically current machine learning, all over machine learning, including something called the deep learning, I will briefly explain later. But anyway, the current machine learning techniques is usually means just an interpolation by curve fitting. And does not mean any human-like, flexible, deep thinking reasoning, something like that. So this is not magical things, just a curve fitting to the given data. And there is no magical ways here to bring something unknowable. So do not think machine learning or AI to be some magical black box. This is basically just fitting to the given data or some sort of tweaking the data, given data. So for even whatever your method is. But the problem is it's just an interpolation. It's not easy task because we should do it. We should start curve fitting in very high dimensional space, for example, 700 dimensions or even more, million dimensional space or something like that. So it's a non-trivial at all, probably. So because of this high dimensionality, so many traps, many pitfalls are there. So I will explain this point. So what should not do it, or what should not expect machine learning. So, but technically speaking, it's a curve fitting in high-dimensional space. So it's very simple in principle, right? Anyway, but it turns out this simple idea is very counterintuitive. So many realistic tasks can be solved by this simple idea. And the first one is something called algorithm. Pixel to pixel inputs the illustration, line drawing into some realistic photos. This is, of course, input-output mapping, but this seems like very non-trivial. Or you can probably, some of you heard of the word deepfake, some social problem, causing social problem, but this program can convert some faces speaking into other ones speaking. So we can swap the face inside the video. And also the similar technique can use this types of conversion. So in this cyclogram algorithm converts horse into zebra. So if we see horses in the video, so all of the horses converted in the zebra very naturally. And also here, we can convert some movie into movie with the box, what is inside. In real time, we can process this task in real time. But this is input. Input is a movie, and output is a movie with this bounding box annotation. So all of this task is basically input-output correspondence, but probably it's some like non-trivial. So that's why machine learning is kind of a core technology of Google, Facebook, Apple, something like that. But anyway, what actually it's very difficult to recognize what is going on inside machine learning, even for us, so even for machine learning researchers. So some problem, for example, probably some of you may heard of the IBM Watson, which is some champion AI programs to win some quiz competition. And now applied to IBM Watson to a healthcare problem or a medical problem. But that causes some under-delivered expectation because of this very complicated reason. But anyways, that's why we are researching machine learning as a research topic. But again, so machine learning is very simple in principle, but why machine learning looks so complicated here? That's because we have many models to be fitted here. For example, if we see this training example, I'm trying to explain this trend by some curve, but many possibilities exist. For example, if we're fitting the line, something like that, or fitting a very complicated curves here, or some more milder curves. So which model is good is basically, we don't know. So it depends on the problem. And basically the many machine learning models exist for the curve models. But which work best is basically depends on the target problem. So only data we have is this black point. So we don't know actually which is better using our very limited data. So we need to investigate the performance more in detail. Anyway, we need to choose appropriate machine learning models for each given data set and even for each given target problem. So this is the most I want to explain today. So this sort of, you can easily search Google machine learning or some machine learning Python or something. You can see the list of many machine learning algorithms, and probably you will feel very unclear which method to use for your problem. But this is basically the core problem of machine learning. So any model can be used for any problem, but which is the work best is very dependent on some subtle factors. We will see that later anyway. So anyway, we have many machine learning models. So if we draw the boundary for this, this is a very standard toy data, which is called moon data set. One class is like moon, and another class is distributed, is like another moon. So we want to build some classification boundary between these two moons. And if we choose the algorithm, for example, if we use the machine learning algorithm called support vector machine, so you will get this kind of boundary. But if you use, for example, neural network, so deep learning, then you will see this kind of a boundary. And it depends on, so if you like a random forest, then you will see this kind of boundary. So, but intuitively, probably the boundary like this or like this would be worse than the boundary like this. So as support vector machine sounds nicer, but it's not that kind of intuition, because in 2D, probably support vector machine works better, but in very high dimensional, things is very become complicated. So it's a very counterintuitive. So that's why we have a very large set of machine learning algorithms, so which is basically have a different surface model. So every machine learning algorithm have different surface curve models. Anyway, and basically for some of you might machine learning a little bit, I will focus on the supervised one today, but many other tasks also are major research topic in machine learning. And also you will see some review paper here. So this figure is basically from this paper by our group. But anyway, so again, the machine learning, in other words, machine learning is a systematic way to find a high dimensional mapping from input to desirable output, just by giving a lot of input-output example. All right? Okay, so in principle, it's very simple idea, simple and lazy idea. So we give up what is going on here explicitly. And also, as you see some example, this lazy idea really works in diverse applications, because most of the cases we don't know the process explicitly. So explicit models, so theory-driven models, have some limitation in the to the real-world problem, because the real world has many subtle factors, many noise factors or something like that. So, and a relationship is very indirect. So in such cases, it's very difficult to come up with some explicit theory to explain every use cases. So that's why the machine learning is now is a core algorithms of machine learning, search engine like a Google. So previously, Google search engine is basically driven on the algorithm, something called a PageRank or something. But now it's most of our search engine ranking is based on the deep learning, so machine learning algorithms, or machine translation from some languages, for translation from Japanese to English or something like that, or self-driving or self-autonomous driving cars, or some personalized medicine, or some advertising, transportation, weather prediction, security, or some very broad field of application is possible by machine learning. And of course, today's topic is science is also targeted. The part of science is also target of machine learning. So, which is things I want to explain later. So anyway, that is what is machine learning. So the next thing is why this machine learning stuff matters to you chemists, because today's lecture is basically for chemical students. So anyways, probably you will not notice explicitly, but science is the way of science, or techniques in science is gradually changing during some time period. So science is always changing, and the tools of, especially tools of sciences are changing. So we can, if someone come up with a new method for measurement, new devices for measurement, new way of, I don't know, new technique of a science is developed, probably the way of doing science is a little bit changed. So that is a normal way of science goes. Then the machine learning is some one tools which is also can change the science a little bit. So we have some review papers, even in the Nature of Science, which is not engineering papers, which is a general purpose paper. So basically, so many people, many researchers in the many field have some interest in machine learning because of science also generate the data, which sounds like machine learning can be applied in some cases. And also, so probably if you are experimental chemist, probably you can understand this part perfectly, because doing science takes time and cost. Cost means if you use a reagent, you need to buy it. So if you measure something, then you need some device, some very expensive device. So basically, science needs time and cost usually, and which is still very empirical. Which means if you to get some nice data, you will come up some experiments, probably inspired by your supervisor's advice or your senpai's advice or something like that. I'm not sure. If you read some interesting papers, so you can come up with nicer experiments or nicer simulations methods, simulation setting, something like that. So if you run experiments or run some simulations, now you get results. So you can check, you can validate the results, what is happening. And you basically your assumption before the experiments or before the simulations, you get some insight comparing your assumption and the results. Then you can feedback that results or the obtained insight to next experimental plan, next simulation plans. And this cycle is a very basic cycle in every science. And especially the Thomas Edison says, like here, probably you can heard of this kind of a quote. But this actually means the experience plus some nice institution makes good science, which can translate it into the you need really incredible hard work, like Edison suggested, plus you need some luck to find something interesting. But now is a 2020, so is this statement is still valid? Because everything looks complicated than Edison's era, right? Edison's era is basically the electricity itself is very new. But now you have many complicated devices or measurements or so experimental techniques or something like that. So probably you might wonder how incredible hard work you need. So probably, so to get to some nice result for a very complicated phenomenon, probably you need more incredible hard work than the Thomas Edison. So it's probably impossible. So we need to implement here. So that's why some researchers have interest in the data science or machine learning or AI here. And the motivation is often related to this fourth paradigm things. There is some books called the fourth paradigms. This is probably open, so open access PDF exists probably available in this URL, so you can see the contents. But anyway, Tony Hay made some collection about this fourth paradigm thing. And the fourth paradigm thing is basically some vision provided by some computer scientists Jim Gray here. So this is a Jim Gray's idea. But why Tunihei, not the Jim Gray, write this book is simply Jim Gray's disappear. So, Jim Gray calls e-science here. So, and gives some talks at some governmental council meeting here. This is a very legendary talk and a very influential talk. And Tony Hay summarized basically this vision and collect some use cases along this vision. That's a book. And anyways, Jim Gray gave a talk in 2007, and he called this new approach called e-science. And this is Jim Gray's view, and there is the PowerPoint of this talk is available. So this is from Jim Gray's PowerPoint file. And basically, 1,000 years ago, every science was empirical. So just do something, observe the result, and consider why that result is obtained. And repeat this forever. But the last few hundred years, there appeared theory like physics, quantum chemistry, or something like that. So gravity, or anyway, there is a theory to explain the things or phenomena. But theories are not enough to explain the problem at hand. Then the last few decades, computer simulations techniques emerged. So computational branches, so we can simulate a complicated phenomena, like how COVID virus is distributed in the room if we cough a little bit with some specific masks or face masks or something. Probably you see it in news or something. We can run some very hi-fi simulation using some high-power computing resources. But anyway, and also if you from the computational chemist, probably you can simulate chemical phenomena by some theory-driven computation. Then that's last few decades things. And the Jim Gray's point is this is the previous paradigm. And today, we should focus on the data exploration, something called e-science, because to unify theory, computation, and experiments. Because we have a large amount of data captured by many kind of instruments, many kind of measurement devices, or many kind of simulations at various levels. Or we have a database software that we can store data and we can search the database, or we can visualize the data, something like that. So why not we use this kind of data to get more efficiently some scientific insight of scientific conclusions. So that is the point of e-science. E means probably electric or something. But anyway, this is the fourth paradigm of science. Jim Gray's thoughts. So that's why at this 2009, Jim Gray also called, we have already various kind of X info, bio info, chemo info, I don't know, materials info, or something like that. So many informatics emerged already 10 years ago. So we have many computational or computer science related problem, how to make use of the data, how to store, how to efficiently represent things or something like that. So this kind of stuff is basically we need to solve by all different principal researchers. So that's why Jim Gray called this kind of paradigm as the fourth paradigm. So that anyway, we are now here to 2020. Then we have probably used, of course, you will see the many data sets from experiments or high throughput experiments or just some experiment published in the paper. supplementary information, or you can search some databases like CAS or something, or reaccess, or I don't know. So you can search and get results from the databases, and also you can run some simulations. So hi-fi simulations from quantum chemical level or some more rough level or something like that. We can access many kind of data now. So we want to unify the result to get the insight, more details. So this is what Jim Gray thought before his appearance in 2007. Let's more specifically speaking. So we have some unknown mechanism here, and probably we slightly know some factors related to these mechanisms, and we observe the factors and observe the relationship, observe what's going on inside here. So observe the data about these factors or these states with the factors. And a theory-driven model. So if we try to explain this by theory, probably we need some explicit model here, some Hamiltonian, or I'm not sure. So some explicit model requires it. So we explicitly build some mathematical model with terms of these factors and states related to some target quantities, some yield or reaction speed, or I don't know, anything you want. But today's topic, data-driven topic, so which is a machine learning AI approach, is basically we're give up explicitly specifying here. So this is just a surface model, so very flexible surface model. Put some very flexible surface model here, and it fits the parameters, fit to the data here. So in this case, usually we can compare the theoretical simulations result and actually experimentally obtained results to determine whether or not theory is correct or theory is at least some relevant. But here, of course, the given data is reproduced because we tune parameter of the surface model to reproduce this data. So this data, given data, is already consistent with the model. So we cannot do some validation like here. So it's a very opposite types of approach. So you need to take care. At least we do not think data-driven approach instead of theory-driven approach. It's a complementary relationship. So, but actually, we have many unclear relationship at many levels. So quantum mechanical level, physical, chemical level, or biophysical level, or physiological level, something like that. So if we put a molecule here, and if we want to predict some property at toxicity of molecules inside human cells, or some protein binding affinity of molecules, or some solubility of molecules to water, or some quantum mechanical quantity of a molecule. So if we can predict this kind of a stuff, we can always apply machine learning here. So this is called QSAR, so quantitative structure activity or structure property relationship, which is the main major topic of chemoinformatics. And I will skip the chemoinformatics things today. But anyway, this is the idea when we have some motivation to apply machine learning. So for example, this is a example of a standard machine learning benchmark data. In the cases, for example, this compound is mutagenic, which is if we put this compound inside the human cells, it causes the DNA mutations in high probability. Such molecule is annotated +1, and if there is no risk to a mutation, put -1. And then we can have many collection of these positive compound and negative compound. But the classification rules, so what types of a property inside a molecule causes this DNA mutation is very unclear. So we can apply machine learning here. So other types of mutation is also very complicated. For example, this is some sort of growth inhibitor. So if we put this compound into some bacteria, then the portion of a bacteria dies accordingly. So if the compounds kills many bacteria, it can be some such compounds for use. But if no effect, that is a nonsense as a growth inhibition. So if we kill the cancer cells, so that can be anti-cancer drugs, at least candidates. But if no effect on the cancer cells, probably it's not related to any kind of that property. So this kind of a task is repeatedly analyzed by machine learning as a QSER program. So in the recent years, also this kind of computational quantities are also targeted by machine learning. Basically, this is a computationally obtained amount. So we can run this simulation in a right way, then we can get the values here. But the problem is that takes much time. So it's a time-consuming simulations in some cases. For example, if we have a very large number of molecules and want to this kind of amount for every molecules, then it's can be very time-consuming. So the people use the machine learning instead, and this paper is very phenomenal, and it claims the prediction error of machine learning models lower than this simulation. So if you're interested in this statement, please check the paper. But anyway, this kind of a trend is emerging recently. So anyway, there is some review paper in the Nature Reviews Chemistry. It's a journal like Nature Reviews Chemistry, or you can. So anyway, you can come up with this kind of task setting for molecules and some properties of interest. Toxicity, from toxicity to some quantum chemical level of quantities. But anyway, and more recently, the focus is more interesting thing is the reverse side of this machine learning prediction. So machine learning prediction is basically input is molecules and output is properties. But the more interesting thing is input is property and output is molecule. So if we want the non-toxic compound, then if we input the non-toxic part here, and if the reverse machine learning generates some promising compound, it's very useful. But so probably apparently from what I said until now, you can just replace the input and output is enough for this purpose, but it's not, because inverse is not unique. So if we inputs this image into the machine learning and want to return what is inside in these photos. In this case, it's all of the photo is a television, TV. But the reverse side, so if we put the TV, then there is infinitely many variation of the TV photos. So this task is not so good for machine learning. But as a settings, this is very important. So this is a machine. If we call this machine learning, so this is something called machine teaching. And there is some many methods for this. Purposes are emerging, but it is still ongoing topics because of this non-uniqueness. But anyway, this is the generation task is also the target of recent machine learning technologies. So, and last thing, we have 30 minutes left. So anyway, this is a very brief big picture of machine learning and why it looks good for some chemists. But anyway, now is a very good time to start machine learning because there is a many very easy to use softwares or libraries. So let's try the machine learning in your browser. And of course, if you have a smartphone, the smartphone have a smart browser, so it's totally okay. And the important thing is that this requires no setup. So if you have a browser, you can run the machine learning. And for this purpose, people use some service called from the Google, some Google Collaboratory. And this is the URL of the Google Collaboratory. But if you have a Google account, probably you can instantly use this one. Or if you have a Gmail account, or if you have a Google Drive account, probably you already can use this service on your browser or on your smartphone. So please access this URL. Probably you will see the screen like this. And anyway, if you click here, you can see some demo. But please click here, so new notebook here. Then you will see the screen like this one. So actually, let's see. So this is some first this is the course website I explained at the very beginning. But anyway, you can get the slide here, and also you can get the code at the collaboratory code here. So if you click here, then you are transferred to the collaboratory notebook, which I prepared for today's course. So something like that. So anyway, you can see some code here, but important thing is, so here, run this in English. But anyway, if you are Japanese speakers, you can use this with the Japanese menus. Right? Today I will use this by English menu, but anyway, any languages you like. And create the code here. And for example, if you input the Python code here, for example, anyway, then click this button. Then this screen is connected to some server at the Google data center, and they run this code here. So this needs to be Python code. But anyway, for example, addition of 1 plus 123, so you can return the code. And also, I don't know. So anyway, you can get the result. So first command is you need to boot some server with background, but after that you can get the result instantly. If it's not computationally demanding command. But anyway, this is a very interactive Python environment. So you can start to learning Python using this command. But anyway, and also if you see the files here, so you will see this here, the table of contents, and also if you click this folder button here, so actually you can mount your Google Drive here. So if you upload your file, your Excel file or something like that to your Google Drive account, and click this button, so your Python code can access that file. So if you have a data and you have an Excel file, then you upload to the Google Drive, and you can use it in your Python code without any setup here. So you don't need to install Python in your PC or in your smartphone. Basically, this all computation is done in the Google's computers. Anyway, and also this is we can put the text here. So, and this is called Markdown. But anyway, So you can get there. And also you can get, you can get the title here. Markdown has some small grammar, but anyway, it's anyway, so you can get some just note without Python code. But anyway, you can mix up your text memo and your report with the code here. This is the point of this collaboratory, or this is a called a Jupyter Notebook in Python communities. But anyway, this is what you already can use. So why not to use here? Anyway, so I'll go back to slide. So this was the Google Collaboratory. And you can click the button here, or just by shift, simultaneously input the shift plus enter. So then you can run the code interactively. So anyway, the purpose, so we have remaining 30 minutes. So let's reproduce the paper review results using this easy to use environment. So this is this is our papers, the machine learning prediction with something called a Deep Center. And actually, I will skip the chemical part because I'm not a chemist, but we have a 2 data set here. And we can predict something called machine learning by machine learning here. This is a prediction by machine learning. This is the amounts computed by the chemical simulations. Anyway, let's try to reproduce this in 20 or 30 minutes here. And anyway, this is a very brief explanation what is predicted in this task. But anyway, this is called something called Deep Center. And the target is something like this one. So in organic materials here, so put some inside some host metals. We can put the guest metals, 1% of a guest metal here. Then compute something called the D-band, because usually these materials consist with transitive metals. I don't know. So which is so D-band is a very characteristic behavior. So some researchers are very interested in how the D-band is. So just compute the just center for this D-band. Then this is a very old paper, 1997, by Noskov groups, the famous researchers probably. This is the computational result of the shift in D-band center. So this is the D-band of the iron, and this is the shift from this energy to plus 0.05 if we dope CO into this iron metals. So this is something like that. So relativity, the clean metal values is indicated as a table. So we just use this table calculated by Noskov groups. And actually, I prepared this data table as an Excel file here. So you can just one line of code to load this data set into your Google Collaboratory environment. So we use 2 libraries here, import. Import means that we can call some libraries. And we will use probably two, in the data analysis situation, these 3 libraries is very fundamental, which is called, first one called NumPy. NumPy is basically the library to handle the numerical multidimensional arrays. And another one is the pandas. The pandas is basically handles this kind of Excel-like 2D tables. So statistics, calculate statistics, load a file, and visualize the data or something like that. So we can use pandas functionality to read the CSV, or even we can read the Excel directory. But anyway, here we just load the CSV file here, then put this variable. You can see you can see the table here. And I'll try. So live coding is dangerous, but anyway. So in here, in this case, we can click here, click here. Then here. So you can see the table. Okay, then this table is basically the nodes. This table, so pink part, pink highlighted area of original papers. And if you load the object as this variable, here's I think a variable name is not good, but I put the my table here. Then the location log something something you can get the value of corresponding cells. So if you get the value of CO, nickel, and I, then you just specify CO here, row, basically row column. So CO nickel returns 0.28 here. If you specify CU, so you can get these values like that. Or even you can get the one single element which corresponds to the row here. So you can get this row, this row here. So anyway, the pandas functionality easily can handle this kind of a table inside Python. So, for example, if you write Python code, if even you know Python at all, probably you can guess what is going on here. So for H in my table index is a row, and the column is the columns. So every index here, and then we put the name H for each, and every column here, we put the name G, that prints the host guest plus the table values here. So you can see that you can see the values in order like this one. So here, this is a double for loop to just print out this table accordingly. And this F is the format. So if you put the F here, then you can replace the format the value of a variable here. If you remove this, just this strings is printed. But if you put F here, then you can, each time value is changes accordingly. So anyway, using this Python code, we can compute the non-relative values of a table we need. So here, this is the clean metal values, and the other values, non-clean metal values, will be the sift. So we need to get the absolute values. We need to add up these clean metal values in for each of our values. So this is clean metal values is if we put the H and G here, then clean metal values is HH or HG if we equals here. So if H and G is a difference, so H here and a G here, then we need to add up host metals values here. So my devs log HH, add up this value into the corresponding value here. So HG, add up to the HH here. Then this table is rewritten as absolute values, not the relative to the clean metal values. So this is a target value we want to predict. And actually, what is input in the paper is something like this one. So anyway, for example, if you want to predict this value, so Fe and Cu are given center absolute value to the field model. But anyway, the absolute value of our given center for Fe, Cu, and Cu is 1% doped into the Fe. And then input variable is something like this one. So each metal has some very basic properties, like, I don't know, atomic numbers or some, I don't know, ionization energy or something like that. So from the chemistry handbook, you can see any kind of chemistry textbook or chemistry handbook, you can get this kind of values. Then this is the ready-to-use values. So our purpose here, or our interest here, is this kind of ready-to-use values can be enough to predict this kind of non-trivial values. And if we try to input the Fe host and into the Cu guest, then we concatenate the two types of values. So Fe values here and the Cu values of the host metals appended to guest metal features here. So in this case, it's, the first part was so this value is from the Fe, and the remaining part is from Cu. So if we set up this inputs, then we can just try the machine learning, because we have many examples. I'm not sure many, but we have many examples here. So let's try to build this table here next. And it's also, I prepared this table also, so you can load this file in the same way as I already explained. And you can see the table here. So this is the pandas object, and if you add a dot head, then the head means first 3 lines is presented. So if remove this one, the first 10 lines is up presented, and if you remove the head, the entire table is shown here. So you can try in your browser. But anyway, you can see the contents of this table easily. Only one line of pandas functionality. And also, in the previous way, you can access the value of the content. So if we get the row of this cobalt features, then you can write like this one. Then this table is, we can build this table like this. So we can first initialize in these tables, the name column is not needed, because we need is from these 8 values after this value. So we drop this name column here. But anyway, after that, we initialize X and Y. So X should be our final input, and Y is the final output. And we add up for each corresponding pair into this list. And the first one is the host features. Is basically feet is this table. This table. We name this table the feet. Then feet log H means the 8 numbers of the host metal, and to convert the numerical array by this command, and also we can get the same information for the guest metal, and then we just concatenate these 2 vectors, append it. Then this should be the input information here. And the output should be the corresponding my table values of HG here. So what we want is if we input this one, then we want this Y value will be outputted. This is our machine learning setting. So if we made up these values, then just add up X values and Y values to this list. And this is a debugger line. So when we if we find H equals to Fe and G equals to Cu, we ask the program to print out this value, so this pairs, and the output is here. And this is exactly same as what we want here. So FECU is input is 82.66, 8.66, 25, 26, 55.8 or something like that. And output is a minus 1.05, minus 0.515. And this input output pair is added to this list one by one. So this is the entire line. This is a debug line. So this is enough to make this list. Anyway, after this code, we just have this kind of table. And if we input here, so 18 numbers here, 9 plus 9 equals to 18 numbers here, then try to predict this output value over the band centers. Right? So this is all preparation. So in a very short record, right? Probably even if don't anything know about Python, you can guess this can be done by yourself. But anyway, the full code is something like that. This one, but anyway, it's a very short, only 28 lines or something. And most of the code is just information URL or just a load file or something like that. So anyway, next we can move on to the machine learning part. But actually, the machine learning part is very short here. And first, we can check the size of the table of X and Y. And X has 121 rows and 18 columns, like this one. So we have here. This corresponded to 19 because I adapted Y here. But anyway, the X part is only 18. So we have 18, and Y is just vectors of length is so one input corresponds to one value. So if we have this number of rows, so Y number should be the same. So, but if we input this all over this into the machine learning, so we can not evaluate that machine learning stuff can predict something. So we split the data into 30 examples. We can hold out the 30 example out of this 121. So remaining 91, only remaining 91 example is fed to the machine learning part. So in the first we need to shuffle the row here. Just one line command from the scikit-learn utilities. I will explain it later, but anyways, we want to shuffle the rows. Without shuffles, we just first part is training, first part is evaluation. But this row is very systematically generated, so it's not good. So we randomized separates to 30 plus 91. So for this purpose, we just the 90 word parts we named X train and Y train, and the remaining 30 part we put X test and Y test here. And the machine learning part is just one line. So we prepared some models. And here we use something called gradient boosting regressor. But anyway, any models can be possible here. And if we load a model, and the just code fits to input example to desirable output example. So X train and Y train is the pair of input and output. So pair of input and the desirable output. So if we call the fit here, then machine learning algorithms try to build a mapping to reproduce X from input X train to X train. Then, so this one line is basically machine learning, the entire machine learning part. And after this fit line, we can use this model to a prediction. So model.predict X train returns a prediction value over data sets we give here. And X test, predict X test returns prediction result on the holdout 30 example. So this part, probably we ask machine learning to reproduce this input-output relationship. So this is, of course, correspond to the white train. But our true interest is whether this prediction works or not. So this is a very typical machine learning evaluation. And this is a matplotlib is another library very often used in the data analysis, which is basically for visualization. And you can see the graph inside your notebook, so on your browser too. And if you input this kind of plot, so basically this is make a scatter plot, and x-axis at the x-axis we put the y train, and y-axis we put the y prediction train. So and also we can put the it colors blue, and adapt another scatter plot, overlay another scatter plot. At the x-axis represent the y-test, and the y-axis x prediction of a test. So we can get this kind of picture, and this corresponds to the figure of a recent paper here. Of course, there is some random initialization values here, so a little bit different from this one, but the trend is reproduced accordingly. The GBR means this one, so gradient boosting regressive GBR is actually used in the paper, and this figure is very close to this one, which means that even for the test, we can get a very accurate results, prediction results. So this is a machine learning, so we can predict. So it turns out we can predict the deep brain center without any computation if we use machine learning plus some sort of a data. Part of the data. So what we did is something like this one. So we have a table of a deep brain center, the randomizedly masked. So in other cases, 30 example, which correspond to 25%. But anyway, the 30% is masked, randomly masked. And I try to predict that these masked cells values by remaining these blue values training set. Then we can get this one. And the papers also tried 6 descriptors. So we have 18 descriptors, 18 variables, but we can reduce the number, for example, up to 6. But anyway, and also we can change the ratio of training and test spread. Even for the randomly masked half of the cells, we can predict, still get a nicer prediction. Or even most of the cells are masked, still we have a positive correlation, positively correlated prediction here. And also we can paper reported some quantitative measurements on this one. So this is basically visual assessment, plus it depends on this random split. So if we try another split, this can be different. So we just tried this split 100 times and take the average over that's the 100 values. And each value is evaluated as something called RMSE, rooted mean squared error here. So which means that the error over this square and the average and the rooted, as I asked here. So here, the y-text square root is basically this is the average of the squared amount. So the dynamic range is squared. So if we interpret the amounts, then we need to take square root here. But anyway, the value is something like that. So this is just import mean square error here. And if we option square equals to false, we can get RMSE. And if square equals to truth, you just get MSE, so mean square error. But anyway, so if we put the RMSE for training and RSME for test for a single shot spread here. Single shot spread here. We already computed this value for values, so we just calculated the measurement of MSE between y train and y prediction train, and y test and the y prediction test. Then we can get the RSME here. And also, if we try to random spreads 100 times, of course, also we can use some very convenient functionality, so shuffle spread. So shuffle and try to split. So number of split is hundreds. This is a number of iterations, repeat it. And for each time, we set the 0.25 as a proportion of a test block. So, and if we call the cross-pal score here, and input the x and input the x1, xy data here, then we can get the value here, 100 times mean error squared error. That's corresponding to the reported value in the paper. So some part of a paper's result is just a few lines and without any setup, any browser, so reproducible. And so I want you to feel machine learning is easy to use. So please try and play a little bit with the machine learning code on the collab. Probably that is enough to understand the contents of these lectures. But anyways, we can build the machine learning models for this problem. Anyways, 18 numbers is input and the 1 number is output. And actually, it turns out that is only one line of a model fit here. So the remaining part, so this is the half, we are running out of time. So this is the end of the first part, but the library I used in the demos is something called a scikit-learn. This is a very widely used Python libraries for machine learning purpose. And they're easy to use, and you can see some example code here. So if you're interested in building your model or tried another machine learning method, please consult this website. So this official website. But anyway, as you can see the graphics, or if you see the graphics, you can, the official website provided the code, how to generate this example in the code. So if you just copy and paste that code into your collab, then you can get the same output as the demo generates. So anyway, this is the first part of my section, and the contents was what is machine learning and why does it matter to the chemist, and how to try it in your browser. And the afternoon session will be also another 90 minutes. And the first thing I want to explain is traps. When machine learning beginners just apply machine learning to your problem. There is many traps here actually, but I want to explain the details here. But I focus on the most important 5 points today. And after that, I will explain which method to use for your problem, and also what is deep learning here. And then also I summarize as some current effort in the research field and the future directions. So, and this is the end of the first lectures. Thank you, and you should take your lunch, please. So let's get started for the last part, so second part of the lecture. And I will start, oh, by the way, okay, so here is some the quick summary of what we saw in the first part. So we will try to reproduce a result of something like this one. So we have this table to be, and machine learning try to predict this randomly masked part from the remaining these blue values. And this random mask is basically we randomly set. Then the machine learning can predict this randomly masked part for this for this program. And you can see the entire machine learning process in action, so which is a very short Python code. So first of all, I want to tell you that to use machine learning is quite easy for now. So please let's play with the code if you are interested in after this lecture. But anyway, the machine learning is basically if we prepare input-output example data sets, then machine learning part is only one line. And I explained the entire process. So actual situations, the most part, time-consuming part is preparing the data and formatting the data and considering variables and reshaping the table or something like that. And machine learning part is only a very small portion of the entire programming code, typically. And you already see that actual program in action. But for this part, the afternoon part, we will see the inner working about machine learning a little bit and some pitfalls to be noticed beforehand. And anyway, if we prepare the data, so machine learning part is something like this. So that if we set some method to use, so here GBR is a gradient boosting regressor, and if we call this from the scikit-learn library as this model, then if you already prepared some input-output example table accordingly, then just call model.fit and it inputs the input example and the desired output here. So machine learning part is only here. And this, you can, of course, change the method, gradient boosting regressor, to another one, or something called deep learning. But anyway, the set of state-of-the-art machine learning algorithms is already prepared in the very easy-to-use library, such as the scikit-learn. So you can try the machine learning algorithm very easy without knowing what that algorithm actually do. But anyway, for some beginners or some primers, which have not so much about the inner working of machine learning algorithms, probably there is a lot of traps, so pitfalls. So first thing I want to explain is that kind of a trap existing everywhere when you try to machine learning, when you apply machine learning to your problem. So actually, there are many traps out there, but I want to focus on the very important 5 point, only 5 point you should know, so all beginners should know. And first thing is this statement: the quality of your input decides the quality of your output. So basically, why applied machine learning is so challenging in many cases, even if machine learning itself is very easy to code, and very easy to use library there for standard machine learning or deep learning. But anyway, still applied machine learning is, in the most of the case, it's includes a challenging part, because basically the practical usage, if we try to use the machine learning in the practical situations, you should know a little bit about machine learning algorithms, as well as you should know well about the target problem. Because first thing we should do is set up the input-output situations. So choose the right framing of the program as an input-output setup. So in this case, if input is no relation to output, so it's a kind of a random relationship, so machine learning will be failed. So you should know that some related input to the output of your interest. So this part is the first hurdle for you to apply machine learning to your program. But anyway, to set up the right task, you need some knowledge or some experience about the target problem under interest. And also, you need to collect the nice training data. So I will explain this part subsequently, but the training data is key to the success for machine learning. And also, you need to assess the quality of the data and also quantity of the data. And also choose the relevant input variables. And also choose the right algorithm for machine learning. And also choose the right algorithm configuration for this part. And lastly, we need to evaluate thoroughly. I mean, from the various aspects. And actually, if you take a machine learning textbook, most of the part is only focused on here. So the details of every machine learning algorithms and how to tune it, or something like that, or plus some set up the environment, like how to build a Python, how to install some Python library to your PC, or some basics about Python and machine learning math, or something like that. But the applied machine learning, the most important part is that before we entered this machine learning part, so here. So set up the right problem and prepare the good training data and set up the right input variable. And I will explain this part first. Now, remember the quality of your input. Input here is, if it's a data-driven, the data itself is input to the machine learning framework. And the quality of your output means the output is a prediction. So the quality of your data we input to the machine learning decide the quality of your performance of a prediction. So this is because we gave up the accurate explicitly programming here. Instead, we just put the example to the machine learning and build automatically to fit the data. So input is a map to the desirable output for given data, but it's not guaranteed that prediction is correct for the data you're not input to the machine learning algorithm. And basically, the computer sees only the data you gave it, so training data. And this curve is a machine learning model, and this fits to the data you gave. So, which means that your data specify the machine learning function, which means that it's defined your output. So which means that if you feed the poor data or low quality data to machine learning algorithms, probably your machine learning prediction is also poor quality. So this is the most important things to keep in mind when you try to apply machine learning to a problem. And basically, everywhere you will see the data-driven approach or something, but the data-driven means that gave up the explicit modeling, and then rather than just gave the data as an example to reproduce that data's input-output relationship. So that data is key for this machine learning curve, because if this training data, this green dots is very bad, so fitted curve machine learning program make no sense probably. Right? This is a very important point. And this is sometimes called garbage in, garbage out. So if you put the garbage into the machine learning, probably your machine learning prediction is also garbage. And here, the input is training data. Basically, data-driven means that data defines this program's behavior, because we gave up the explicit programming here. So how about these three cases? We have various kind of training data. So first example, seems some trend between the x and y, and if we fit some curve, any curve, like here, for example, then the kind of this curve would be good representative of a training data. So capture the trend of the training data here. And seems like enough number of data we have. So, but how about in this case? So can you see some trend here? Underlying trend between X and Y here. So, and of course, if we put this input data to machine learning algorithms, machine learning anyway fit the sum curve. For example, something like this one. So what do you think about this case? So probably so results. So, but too early to say this is conclusive or this is very nice prediction or something like that, because the number of data is rather smaller than these cases. So we have some margin. Some of the data set is very incorrect or very noisy or something like that. And last example here is almost a random relationship between X and Y. But even for these situations, machine learning try to explain all of these points, something like this one. But probably this kind of fitting is very invalid in most of the cases. Sometimes we need this kind of perfect prediction for a given data, but in the most of the cases, real-world data have some noise, contain the noise level. So fitting precisely to reproduce even the noise level randomness is invalid. And at the first place, X and Y seems like no correlation between the X and Y. So at the first place, this kind of fitting is valid or not. We need to be careful about applying machine learning in these types of data. So this is basically garbage encounter. So if it's garbage, probably, if it's garbage, machine learning don't care. So anyway, the machine learning programs reproduce the training data very precisely. So even in this case, we can have zero training error. So the first thing is basically always to carefully look at your data. So how your data is distributed. So what range and what distribution of your data points are. And again, this kind of stuff can be easily done with some Python library. Here we will use pandas, and in addition to the matplotlib for visualization. And for example, this is a pandas data frame, which is can accept easy to access the row, columns, or cells, or something like that, or subtable, or something like that. Then if we have a pandas data frame, then you can see the contents here. So you should take a look at your data. For example, in this case, we are the synthetically generated. So first part of our 8 here is the table of iron from 8 values from iron. So and 0, 1, 2, 3, all of the host matter is iron. So this first 8 numbers are the same for up to 11. So we have 11 elements in the original data set. So this is, you should be careful about this situation. But from here, the sum values may change. So only half will change. If we either keep the same host matter and but changing the guest matter here to doped 1% into the host matter. But anyway, you can see that this kind of, you need to know this kind of stuff beforehand you apply machine learning. And also, pandas have a visualization function about the data stats with the visualization by matplotlib. For example, And the df here is a pandas object called data frame, which means almost correspond to the Excel table. And in the Excel table, for each column here, for example, you want to know the histogram of these values or some box plot like this, or box plot like this. So this means range and mean and percentile of the values of a variable x8 or something like that. So which means that if we, without any normalization, so dynamic range of each variable is very different in this case. So probably you should consider any pre-processing to normalize the data range or something if you need. Or you can plot the data here, or you can take a scatter plot to 2D plot, take one value and the two value here. And also, just code described, you can see the number of values and the mean of the values and the standard deviation of the values, minimum values for and max values, and percentile between min and max here. So just load the data as a pandas table, and call describe, you can get for dynamic range of each values. Or you can see the histogram just dot hist. So in this case, we just focus on the subset. This consists of two columns correspond to x8 and y. But anyways, you can see the 3 or 4 columns or entire columns to get the histogram. And or you can see the correlation to between the variables. For example, in this case, we just see the correlation of each values to a target value y. So you see some negative, some positive correlation. So this task called explanatory data analysis see the basic stats and some visualization to get the information about how data are. And also with some another library and often popular libraries, for example, this is that we use two, Seaborn and Plot3. And for example, Seaborn have made some fancy plot like this. And this is a pair plot, and this is a heat map plot of a correlation matrix. And even we can see the interactively, so data distribution in the scatter plot here. So this is another library called Plot3. And Plot3 itself is a more low-level library, but Plot3 also provides the Plot3 Express, which is a very easy-to-use interface to Plot3 library. You can get some fancy visualization output using this kind of standard library in your collab environment. Anyway, this is the first thing you need to keep in mind before you try to apply machine learning to your data. And the next thing is training data, validation data, test data splits. And first problem is you see that this situation is invalid for machine learning to apply, but this looks good setup. But how can we quantitatively know that this curve, this machine learning models, the prediction performance about this machine learning model is better than this one? Because given data here, green dots, the error means the gap between this dot and this curve. So which means this curve perfectly explains the given data. So prediction performance on the given data is 100% accurate. This one is a little bit small error here. So in terms of given data, this is also looks very good because no error. But probably you instantly recognize this causes bad outcome. So how to detect this kind of difference? And this is the standard way of a machine learners to resolve this problem. This is called train test spread. And just as we already see in the previous example, that we randomly hold out some data. So say here, the 33% here, so 10. So out of 30 data, we hold out 10 data for test. So this 10 data point will not be fed into the machine learning algorithm, just used for evaluating prediction is correct or not. So here, both examples, we just prepared some portion as a test data set and apply the remaining blue points here, like this one. Also, error for blue point is both curve give some very small error for the given point, but if we evaluate this curve by the held out data point, red point, then this pink curve and the error between this pink curve and this red point is still small, but here we see the very large gap between the pink curve and held out data here. So in this case, the test error is very large in this case. So this curve is not well generalized beyond the test given data. So in this way, we can check the prediction performance using the held out data. So we keep some portion of the data and will not be fed into the machine learning training. So basically, our true interest is some sort of incoming, the performance for incoming data points, which is should be measured by the test error, not by the given data point. So if we measure the test error by using the training data, so the data we give into the machine learning, then this, even for in this situation, the machine learning looks very good. But it turns out it is way bad because test error is very large. So always we need to evaluate it by some test error. And also, we should keep in mind that making training error 0 is very easy. Just to, for example, in extreme cases, we just memorize training data and memorize all relationship between the input and the output, then just return the memorized output. Then we have a zero training error. But this way has nothing to do for not in the memory, so not presented data. There is no prediction capability. So this is not any learning. So, but technically speaking, the lowering small training error is not that difficult. So if we see that training error is very low, we feel happy. We may feel happy, but that is a very half of the machine learning. So we see if the test error is very low, probably that's prediction will be useful. And in this situations, probably if the problem is well posed, then the test error are always larger than the training error, because machine learning is try to reduce the training error by tuning the parameter inside. Then we see the training error is a small training error is so as a matter of course, because we pose that to minimize the training error to build the computer program part automatically from input-output example. So in this case, the test error is always larger than the training error. But ideally, both training errors and the test error are very small, which means the machine learning models will be generalized beyond the the data we give, and probably have some practical usage of that prediction. Okay, and here we see the very weird example to think about what machine learning do. And here X is two numbers here, 1 and 3, and desired output is just the addition of the two numbers. So if we input the 1 and 3, output will be 4, and the 2 and 5, output will be the 7, like this one. Then if we perform the machine learning here, as usual, just dot fit x and y, x1 here, then we can predict the training error, predict the addition result prediction. So in this case, for example, we give the training error here, and we use a linear regression model here. I do not explain in detail, but anyway, then we easily see the training data prediction is very correct. So 1 plus 3 is 4, 7, 14, 30, 11. So our machine learning model learns addition just by giving the 5 example here. Is that correct conclusion? So let's see that more. And for example, using this model, we can try the reverse input. So we give 1, 3, 2, 5, 5, 9. But the addition of a 1 plus 3 is equals to 3 plus 1. So let's try this one. So 3 plus 1. And again, machine learning model returns the correct answer here. So 3 plus 1 is 4. 5 plus 2 is 7. 9 plus 5 is 14. Right? So machine learning understands the reverse symmetry of addition. And remember that this pair, we don't feed this pair into the training. So this is the data outside the training data. And even if we input the unseen example here, 1 and 1, machine learning model returns the correct answer. 2 plus 9 is 11, and 45 plus 1 is 6. And even for a very large number here, then if the correct answer is here, and machine learning actually return the correct answer only by giving this 5 example. And this is a cool thing or not? So please consider this situation. And key is actually the model we used. And if we switch the model to, for example, something called the extra trees regressor here, and they do the same thing. And this extra tree regressor can reproduce the training data for 7, 14, 30, 11, but reverse inputs, its behavior very bad. So 3 plus 1 is a 7.33, and 5 plus 2 is a 7.97 or something like that. So totally misunderstood the addition, the concept of addition. And even 1 plus 1 is 4 for the extra tree regressor, and 2 plus 9 is 11.66 or something. And if we add a very large number, it's returned a very small number. So very weird addition concept that machine learning learns. See, the training data, for training data, we see the 0 training error, but we see the very bad result for unseen data for any possible values. So that's why we need to evaluate this stuff. And in this case, we know about the addition, so we can evaluate that this behavior is plausible or not. But if it's a application target problem is more complicated, we trapped by this situation without very, very careful assessment. And tried some deep learning here for very simple 5-layer neural network. Then again, the very situation is weird. First of all, the training error is not 0. So it's not 4.31 or something. That's not exactly 7.16 or something like that. So slightly wrong. And also, for unseen example, very bad results. So it's does not matter which algorithm to use. It's a very complicated situation. So algorithms and data, and how we gave the training data here. See? Okay, so and the next problem is typically, in addition to training test spread, we often use another part. So that is called validation data. And this is used for something called hyperparameter tuning or model selection. And I will explain this part. And this part is probably the most tricky part for the beginners. And anyway, the machine learning program is a kind of a tunable surface model or a curve. So if we change the value of the parameter inside, then the shape of a curve or shapes of a surface gradually changes. So then the tuning parameters is basically the best fit to the given data. But often many complicated models have something called the hyperparameters. And these hyperparameters are basically not estimated from the data. And I will explain this hyperparameter thing. But this is so this is the next topic. So before that, I will explain something called cross-validation. And if we set the random training and test splits, then it is the training data part is only used for evaluation. Then if we have a small number of data, it's very difficult to split. So we will use something called the cross-validation. So first of all, available data is split in the same equal size block. For example, this is we separate this data into the K blocks here, and held out this block, and the remaining part is used as training data. And unlike the simple training test split, we can exchange the test and the training data block by block. So in this case, if we use the test subset 1 for test data, then the remaining part can be used as a training data. And also, we can try in the case where subset 2 is used as a test data, and the other remaining part is a training data. So in this case, we have a K training test split, and also we can, for example, accuracy or some error measurement, get the K values, and the averaged K value can be a very good measure to assess the prediction performance of machine learning. So this is called cross-validation. So switching the role of test and training. And also, this can be very easy code here. So scikit-learn has a module for cross-validate something. And if K equals to 5, so we split the X and Y into the 5 equal size block, and switch the test and training role. Then in the average, this scoring. This is a negative of our SME, so root mean squared error. And then we can get the training error and test error here, just by taking average. And this is negative value, so we take the negative here. Negative because this is, I think, a technical reason. So negative smaller, or some measure is we want some measure to be maximized and some measure want to minimize. And but as a framework, they want to consistent. So some measure is negative, and then we can compare as minimize and maximize. So this is a very technical, subtle things. But anyways, if we neg here, we -1 here. But anyway, take mean, and then we got a very good measurement for performance. But for validation data, if we need a validation data, we nested this cross validation inside the block. So for subset 1, we have a training data, except this all of the blocks except subset 1, then we split this data set into some other subset, and also some subset used as a validation data. And this is very time consuming, but the most reliable evaluation. So if you have a time and your model on data set is median level, then you can try this, always try this. But this takes a very long running time for very complicated problems. So we take care, very careful if we use only this training test spread. But anyway, even this nested case, we can just use this scikit-learn accordingly. But I will explain this for now. But anyway, the scikit-learn has this kind of some selection of sampled. We will already see the shuffle spread, so do the fixed number of times of the random spread. But anyway, we can do some cross-validation, k-fold cross-validation, split the k blocks, and switch the row. Anyway, if you need it, you can see this kind of a document and usage examples. So the next part is one of the things I want to emphasize: the Turing hyperparameters. And for now, I will just use this, for example, Gaussian process regressor without any specification of an option. For example, I will use I use the gradient boost regressor without no specific option here. But if we print this model object, actually the many parameters already set as the default values. So something called alpha is set to the 0.9, and something called the learning rate is set to 0.1 or something like that. But these default values are basically no guarantee to be optimal or very good for your problem. So we need to tune every parameter listed here. And these parameters basically they're called hyperparameters. And this is needs to be specified by user and not automatically fitted by the data fitting process. And because this is a kind of meta parameters. For example, when we try to fit the polynomial functions, so some values plus some value times x plus some value times x squared, and like order to the p, so x to the p, then the parameters are basically parameters to be tuned to be fitted to the data is basically these coefficient parameters. We have a p parameter here, and these parameters is fitted to the data during the training process. But this parameter p, so the order of a polynomial to be used in the model, is not fitted to, we cannot fit this parameter by the data. Because for training error, if we try the larger value for p, that includes the previous model. So larger p can be more flexible, the curve. So hundreds order can be fitted to any given process, but it's too complicated probably. So this parameter controls the model complexity, the complexity of the curve, and needs to be specified beforehand that we applied machine learning to your problem by user. So we see if we use a p, we can only fit a line here. But if we put the 3 here, we can fit the cubic functional here. And if a fourth order polynomial function is fitted there for green cup here. And if we use a 10, we see the very flexible curve and probably zero training error. But probably this is too complicated for this problem. Then anyway, this kind of meta parameter is called hyperparameter, and that needs to be specified beforehand the training process. And important thing is which model we use is basically depends on the data and your program, and we need to consider the trade-off between very low complexity model and high complexity model. So simpler model is the low risk for overfitting, but sometimes it's underfit because this is a curved trend, but if our degree is only 9, so we cannot reproduce this kind of trend. But if we use a too complicated model, and this is too much, so this part is no guarantee. And we need to some right choice for the complexity. And this is done by the hyperparameter tuning user. And most of the model can have a meta parameters to be control this kind of a model complexity here. An exception is a linear regression. So if we try to fit a line or a line of surface, then there is no hyperparameters. But the other models or most models have some hyperparameters to be appropriately tuned. So the important thing is which, for example, we can see that a different model uses a different function shapes. For example, in this example, we see the gradient boosting regressor, subtle vector regressor, linear regression, and Gaussian process regression here. And curve shape is very different, right? And it looks like this red curve is really fitted to this data set, but remember the high dimension can be counterintuitive. So in this lower dimensionality, probably the continuous model like a Gaussian process regressor here perform very good. But in high dimensional, even for this stepwise function generated by the gradient boosting regressor is gets very high performance and better than the, for example, sometimes very good, better performance than these continuous functions. So it's can be very counterintuitive. And also, if we fix the method, for example, SVR, support vector regressors, then this has some hyperparameters to return. And if we just change the value for two hyperparameters called gamma and C, then you will see the complexity of a curve within the single same model can be controlled. And the red curve is too flexible. And the blue line here is very too simple. And we need to tune appropriately in between. And why we need the validation data, which hyperparameter is good, is basically the situation like this. So the seemingly training test spread is enough. But for example, let us consider determine these cases. So if we have a training data here and test data like here, and if we fit two models here, model 1 and model 2, and of course, if we evaluate its performance by test data, probably model 2 is better than the model 1 because well fitted to in here. But this region lacks any training data, so it's a kind of cheating. So seeing the answer to get the answer. So for example, if we remove the training data here, so difference between model 1 and model 2 have no reason. This is the kind of just by chance factors, random factors, because the terminal 3 model, so this is the end of our available data. So this is we have no guarantee, no evidence to determine which is good. But by chance, if we have a test data here, we can see the unknown. So unknown means the model 2 is perform good over the test data. But this is kind of cheating. So this is called data leakage, and which result in a very bad model building because the test data we cannot access, assumed to be we cannot access, but actually we use this test data to tune the hyperparameter. So this is very not good. So that's why we need to the validation data in addition to test data. That was a validation data here. So, and the next one is identification and the design of input variables. And this is also most of the important things. And in addition example, for example, if you need addition, basically all of the programming languages have addition as a grammar. But anyways, if we need to define addition as a function or subroutine, then typically we should just add the two argument variables and add up and return it. And we can, if we define this one, in Python, we can just call the def. But anyways, if once you define this function, we can call this function as any for input. So if we input any variables, you will see the addition of these two values here. And also, if we use a linear regression, we can have a perfect same behavior function like this one. So if we fit the model and give the 5 example here, and then the machine learning prediction returns the machine learning prediction as an addition result. And anyway, the same result. There is a very small numerical errors, but anyways, it's a very still useful accuracy. But in this example, of course, we should not use this version because we have addition. We understand perfectly what addition is. So we should use this one. This is the first and accurate. But this one is have a risk to be inaccurate and not that first. We need to fit into this linear regression model and calculate the surface height in this line. But so first thing you should keep in mind is this part, machine learning, try to approximate the relationship by input-output relationship, probably something like too unclear to be explicitly modeled, like a face recognizer, spoken word recognizer, speech recognition, or image recognition, or something like that. Or too complicated to be explicitly modeled. We know there is some rule, but it's very difficult to perfectly model everything because of too many factors or too many subtle factors or something like that. In this case, probably machine learning have some practical merit. Or simply it's very time consuming. The machine learning prediction is slower than the just addition, but very quick usually. So if we like this function is simulating in very precisely using very heavyweight, time-consuming simulation, then probably if we can build a higher accuracy machine learning approximation, then that's might be useful in some cases. So this is we need to where to use. We need to consider where to use at the first place. And this is very important to successful machine learning applications. But in other words, we can input this framework everywhere. If we see this unclear input-output relationship inside your problem, inside your code, or somewhere, and you can prepare some representative input-output examples, then you can always go for machine learning. Okay. And variable, so which variable use as an input is very important in this sense, because machine learning model here is just a mapping from input to output like this one. So if we call this model as a function f, and this is a p-dimensional function which outputs the q-dimensional vectors, which means this is if we miss some values here, then that factor cannot be considered in machine learning. So if you want machine learning to take into some factors or some effect, some side effect or something, then you need to input some variable here. having that relevant information. Okay, so if we only use a very limited, only small number of variables having the very limited information, probably machine learning just try to capture the superficial input-output relationship. That is not good for nice applications. And I will skip the chemoinformatics part today, but for molecular or for reaction or something, there is many types of variables developed. This is called descriptors. And you can see some softwares. And probably Professor Bernick's topics might treat this kind of stuff. But anyway, for given problem, probably some previous researcher came up with some descriptors. So you can use, or you can do survey on your related problem first. And also, if you get the two values, for example, add up or divide or difference between two values can be another variable. So that is called feature engineering, but this is also important, and there is some books for best practices. But anyway, this is a very detailed technical thing, so I will skip this part here. And the last part is this statement: correlation does not imply causation. And first of all, machine learning, as I said before, machine learning finds any input-output correlation in high dimension. So try to map input to desirable outputs building this function. And please keep in mind, this does not directly mean underlying process is approximated by machine learning. So which means that this does not directly mean any causation between input and output. For example, the current machine learning can solve all of these tasks in very high accuracy, but still, we don't know what is going on in our inside. So, for example, we can recognize object inside vision, so visual images, but we are not sure what is going on inside our brain. But anyway, machine learning can solve this task. And the ways can be different from our way is happening in our brain. But anyway, machine learning can solve this task using the input-output correlation inside a given training data. But this does not mean causation. So cause and effect result. And a more intuitive result is this one. So this is basically this sentence is often appeared in the very first section of applied statistics. And for example, this is the data I made from a website data, and this is a Japanese professional baseball players' height and weight. And you will see the taller players have some larger weights, of course, right? Taller player have a higher weight. But this does not necessarily mean that if you gain the weight, but this not cause the gain your height. So if you eat up too much lunch every day, probably you will be fat, but you will be not tall. So there is a positive correlation here, but this does not mean the causation. So which means that weight cause height is a wrong conclusion. So do not consider or do not interpret that like that. This is just correlation. See? So this is a typical trap when we try to machine learning and expect something, some insight from the machine learning outcome. And another example, famous example is here. So x-axis is a chocolate consumption in the countries, and y-axis is a Nobel literature, the number of the Nobel winners per 10 million population, which looks like a positively correlated. And Switzerland have a high chocolate consumption and a large number of large percentage of Nobel winning results. But it does not mean that eating too much chocolate, you can get a Nobel winner, Nobel award. So this is a correlation, not a causation between. So do not have this trap. And this is another example, this famous example in the National Geographic. And this is a red line is US spending on science, and the black line is a suicide by hanging. So if a US government increases science budget, then the number of suicide by hanging is increasing. But this is just a random coincidence. And another one is the number of people who drowned by falling into a pool versus film Nicolas Cage appeared in. So if the Nicolas Cage appeared in the multiple films in the year, then the large number of people died by the pool, by drowning. But this is probably completely coincidence. So do not have a. So from this result, we can see the correlation, the risk of having correlation, even if there is no causation. So we need to be very careful about just observing this kind of data when we try to apply the data-driven technologies. So that's why the data-driven approach is to try to approximate this unknown mechanism, but they're not always successful. So be careful about this conceptual difference between the theory-driven approach. And the very famous statistician David Hand gave some words like here. So theory models can be wrong. So if you come up with some theory, and if that theory cannot accord with the experimental data, probably that theory will be wrong. So anyway, we can know the theory, we can evaluate if proposed theories are correct or not. But problem of a data-driven model is we cannot be wrong or even right. So data-driven model, anyway, they try to fit the given data. So machine learning model can perfectly explain the given data, so give all available data. But so we cannot know that is wrong or that is right. Rather than that kind of aspect, basically the machine learning approximation can be intended to be useful. So if this approximation is useful in some context, probably machine learning have a chance to be used. But if not, too much expect on the machine learning is kind of risky because of a gap between the correlation and the causation. So be careful about this gap in practical situations. Okay, this is 5 things I want to deliver to you for some beginners. And basically, it is very difficult. It is very risky because machine learning, just to use the machine learning is very easy, as you see. So if we ignore this aspect, it can generate a very misleading results. So be careful about the data, handle data. So anyway, the next step is a standard machine learning pipeline and some deep learning stuff. So if the data and the setup seems right, the next problem is what machine learning algorithms should we use for a given problem. And this is a recommended pipeline here. So if your data is something like this one, so tabular data with some handcrafted or manually chosen value over here, measurements or some handcrafted amount by calculation or something, then probably you can use the standard machine learning pipeline. But if some raw signal data containing the full observed information, like images or like sounds observed by microphone, images observed by the camera, then you can another option to apply the deep learning. So we split these two scenarios. In the first, well, I will explain this standard pipeline. And probably for beginners, most of the cases, except the images and the audio, probably you should use this pipeline. But your target is images or audio signals or some sensor signals, the raw observation, then you can consider the deep learning. But first, I will explain the standard pipeline. So in principle, it's very simple. We should start with the smaller models. So the first one is a constant prediction. For any input, we output the constant values. So which means no learning here. This is the worst case baseline. So even some performance measurement is worse than this dump. I don't know. This is a very same baselines. Then it will make no sense. So we should try the constant prediction, as we see later. So for classification problem, so to predict the category or some yes or no or something like that, then we just predict the most frequent classes. Like if we use 10 handwritten digit recognition, and by chance our data have a lot of 8 inside, then always predict 8. Any input is 8. Then we can at least give the correct answer for the inputs, which is 8. This is a minimum requirement, but this is the minimum baseline. For regression, very good way is always return the average of the training data. So let's we will see that these kind of sloppy, or this is I don't know. So sloppy idea works. And the next thing is a linear prediction. So the output is a weighted sum of linear variables. And for classification problem, we can use something called a logistic regression. And for quantitative amounts for prediction of real numbers, we can use basically a linear regression. And we have another variation of a linear regression called RIKEN, lasso, and PLS. But anyway, we can try the linear regression here. And also, there is a large number of other methods inside the scikit-learn or machine learning textbook. And the first, we should try the nonlinear models, but there is many nonlinear models, and probably we should start with the simpler nonlinear models. And for classification problems, probably we can use a k nearest neighbor classifier, and also something called the extra trees classifier and random forest classifier. And for regression, we can use extra trees regressors and random forest regressors. And because these methods have a small number of hyperparameters, and the results is not so hyperparameter dependent. So even if it default parameters, probably these models can return the social result for your data table. So if the complicated model that requires very careful hyperparameter tuning is the worse than these models, probably we can use this model. Simply, this is a simple answers. And other models, everything else, including deep learning here, such as the model here, basically requires careful hyperparameter tuning. So requires some knowledge about each algorithm, how each algorithm behave. But for these algorithms, probably very good for beginners, because if we set the wrong hyperparameter for these models, probably still you can get the nicer prediction performance. So anyway, so this start with the smaller models, then try the complicated model gradually, and after confirm the previous low complex model is the high complex model perform better than the previous models. So if we performance is saturated, probably simpler model performs better in the practical situations. And for example, this is, I will explain the, I will skip the code, but this custom function validate model just input, that's take models and throw it to the cross validate with debug centers data. Then that returns the training and test measurements. So if we put the dummy regressors, just returns the mean of the training data, then we can see that this value, 0.8 RNSE, is possible. So if we see some performance measurement worse than this one, this is that was something wrong. So that does not make any sense. Then we should try linear prediction here. So linear regression, ridge, lasso, and PLS. And PLS actually have some hyperparameters. But anyway, if we see it for the event center problem, important thing is that linear regression is enough. And we don't need to use a ridge, lasso, PLS, which have a hyperparameters. I don't, in the paper, we tune these hyperparameters, but here we set arbitrary value here. But anyway, probably you will notice a linear regression performs social result 0.226. So if the constant number is 0.8, so it's improved into 0.26 here. And also, you can try the simple nonlinear prediction here, extra trees regressor and random forest regressor here. Then performance is a little bit improved to 0.21 and 0.23. So the extra trees regressor performs better than the random forest regressor and the linear regression here. And also, of course, this is a constant prediction. And then we can try the more complicated model here. So probably supplies most of the complicated model perform worse or perform very bad here. For example, gradient boosting regressor achieved 0.14. This is the best result here because so far the best result is this extra trees regressor, but it is improved into 0.22, 0.14, then this is the best. And we use this method in the paper, but other method called SVR, Gaussian process regressors, the neural network on kernel rate regressors, performs bad, the worse than this dummy regressor, so constant prediction. So it means that it make no sense to use these algorithms. You need to more carefully tune or give up to use this one. And actually, I didn't mention the pre-processing here, but for this method, it's very dependent on the scaling of variable ranges. So at least we need to pre-processing to be normalized at input data to improve these values. And if we try a little bit, then this is worse than the constant prediction. But we can improve it to so-so 0.3, 0.3, 0.4, 0.3. But this value is worse than the linear regression value. If you just use a linear regression, we can get 0.26. So we don't have any reason to use instead SVR, Gaussian process regressor, neural network, or kernel rate here. This is a kind of a standard pipeline of machine learning algorithms. Okay, so please start the smaller models and gradually try the complicated models, because that requires careful hyperparameter tuning. Then the last 20 minutes, I will explain briefly what is deep learning and what it's good for. So the deep learning is basically kind of a multi-stage model of this kind of steps. So deep learning consists of small calculation units, small function, last addition, multiplication, or just apply some thing univariate function or something like that. So combine this elementary computation as a network here. And if the resultant network is very deep, then it's called deep learning. So deep neural network, learning by deep neural network called deep learning. And basically, this approximates the transformation of input representation into more better representation. So if we do not use the deep learning here, then standard pipeline is come up with some input variables here, so P variables, and manually, but we need to manually design nice descriptor or nice input variable here, and then we can feed it to the standard pipeline machine learning here. So extra trees, random forest, or SPR, or something like that. But instead of this manual procedure, we can approximate even this procedure if we raw observation is available. So for example, image is full information to guess what is inside in the images. So for sound is full information that's containing what is spoken, a word or something like that. And but the input images is just an array of raw observation is not good for usual machine learning input. So we need to convert input images into some more appropriate representation by the multi-stage function. So F1, F2, F3, F5. So F1 converts image a little bit, and that's fed into the next module F2. And F2 converts that image a little bit, then fed it to the F3 or something like that. So F1 to F100 have a 100 layers neural network, and that is called deep learning. So see the more intuitive examples. So we want to assume that we want to classify this moon data set. So input space is the XY plot, so 2D, and for simplicity, we just draw a line for this location, and the blue location is just represented as this line. So let's apply deep learning here. Then machine learning try to find good representation, gradually transforming this input space into find more separable representation. So if we find a nice representation, well separates the red point and blue point, like here, then just linear regression is enough to correctly classify red point and blue point. So, but point is that the deep learning works like that. But the point is that this approach is not always successful. So see this example here. So in this case, so blue line and red line is deep learning tried to find good representation, but basically failed. And problems looks more complicated than the original. So in this case, the deep learning performs very bad. So if the deep layers neural network part find a nice representation for transforming input representation into more nicer representation, then the task can be more easily solved by more simpler machine learning method. But if it's failed, it can be very bad. So this is the core idea of deep learning. And of course, the most typical application is the image recognition. And as we already see an example, the handwritten digit recognition can be solved by deep learning. So if we fit this 784 numbers here into 10 numbers which represent the probability for each class, 0 to 9, then we can put up machine learning here. And of course, we can try deep learning in this case because the input is the images, and this includes the full information about the handwritten characters. And actually, there is a very famous benchmark data set called MNIST. MNIST is a handwritten digits data set, something like this one. And you will also notice that this is the example of a subset of an example that's labeled of a 7, but some 107 looks like very much 1. And I'm not sure this can be recognized as 7 by human, but anyway, some looks like 1, and some is, I don't know, looks like different alphabet or something. But anyway, we want to try to solve this problem just by machine learning. And if we use deep learning is also very intuitive. Here we use the package TensorFlow Keras, but another popular package, or I use for research is something called the PyTorch. But anyway, there is many popular Python packages to be available. And again, for example, this TensorFlow Keras can be called by like a scikit-learn. So just after build a model specification, then just model fit is enough to build a mapping between input and outputs. And if we try to predict something, we can just use predict. Then accuracy is 99.25%. So it's a very accurately prediction. And full code is, I put the full code into our collab file. Then if you are interested in the deep learning, you can try that simpler method, and you see some other example code of a tutorial of Keras or PyTorch or something. But another thing I want to mention is here we can have a 99.2 accuracy, but of course, anyway, if we try to use this one, you can set up the GPU environment, choosing runtime and change runtime, and GPU or TPU. Then you can freely use GPU to some time limit. But anyway, for this kind of simple example, probably you can freely use the Google Colab TPU or GPU environment. And you can compare it just by run over the none, which means the CPU execution, compare with the GPU or TPU cases. But anyway, you can try this code after this lecture. And I also input the monitoring code for the training process. So final accuracy is a kind of 99.2, but it's a gradually obtained training process of our deep learning. But anyway, the important thing I want to mention is that we can, of course, use the standard pipeline instead of deep learning here. And deep learning actually achieved 99.25. And if we try just dummy classifier, so constant prediction, test accuracy is 1.0, so 1% of our accuracy. So 1% is almost random because we have a 10 digit. So random return numbers probably around 0.1%. So this is a 10% is almost random. But anyway, for example, if we try a linear model, we can achieve 92.5%. And sometimes the difference between 99.2 and 92.5 can be acceptable. And linear regression is very simple. So if you're not be bothered with the deep learning things, you can instead, 92% is enough for your application. Probably you can use linear prediction instead. And also the k-nearest neighbor classifier or extra trees classifier achieve around 97% almost. So and the difference between 99% and the 97% is mostly acceptable. So, and it's very fast. So you can use k-nearest neighbor takes time consuming, but extra trees really are first algorithm. So you can use the extra trees instead. And the last one is another library, popular library called LightGBM, which was developed by Microsoft. But anyway, in this case, you can have 98% almost for moderate CPU times. And also, this is a time by only the single CPU. And if you have the recent laptop have a multi-core CPU, if you run this on your computers after the set of a Python environment appropriately, then you can get more shorter time. So you can always think alternative solution by standard pipeline if your problem looks like a deep learning related. Anyway, this is deep learning things. And last things is sum up about recent research topics and the future directions. And be careful about the data handling because machine learning model is just representative of training data. So out of the scope, that if data set falls in the out of scope area, there is no guarantee the machine learning prediction is accurate. So but we need to be very careful about this point because in high dimensional, so the distinction between the it's a training data set area or outside of the training set area is a very subtle. So it's very difficult to recognize. So we need to be very careful in principle. But the problem is in chemistry or in material science or in drug discovery, basically we want something in a training data, of course. So new drug, new chemical reaction, new, I don't know, compound or something like that. So if it's a revolutionary results, then it should be observed, not observed in the available data. So this is there is a large gap between the machine learning, what machine learning can do, and what we want in the science like chemistry or material sciences. So what should I do? What should we do? What can we do? Then the important dilemma, very basic concept called exploitation trade-off is a very important concept to consider this one. And machine learning is basically try to exploit the available data set to spot the plausible region. So if we want to maximize the Y, probably the next experiments should be around here because compared with the other area, this area can have a higher performance Y. But also we need to probe the untested area. So like here. So here we have a sample, but here there is no data. There is no data in between this training sample. Here there is no data area here. And in high dimensional, most of the area is untested. So we need to explore regions potentially having better Y, but are not yet covered by the current data. So we need to take balance between exploration and exploitation. And this is required or a core concept to perform this task of a reverse design. So machine learning is try to predict a property, but we want to have some input that have a desirable properties, like a drug discovery or new reaction development or something like that. So there is the state-of-the-art machine learning algorithm can try to tackle this problem from various aspects, but this is ongoing topics. Anyway, this is there is a subtle things to need to consider this trade-off. And another aspect is from deep learning. So machine learning is basically interpolation, so interpolative, but machine learning can seek the other input representation by a neural network or something. So interpolation in this representation can be different interpolation in this representation because this is a very transformed appropriately. So if we consider the interpolation this, that can be somewhat exploitative inside input region, input variable representation. So deep learning can play important role for extrapolative discovery, because we want something in the data set, so we also seek for a nicer representation for a given task. So for this task, probably the development of a deep learning technology is very important, considered to be very important. And also, this is depends on the input variable. So that's why feature engineering, so development of a feature design and come up with some combined feature, input feature in some various way is very also important, influential in practice. So this is another aspect. And the remaining part is basically recent review. So autonomous discovery is coming. So available high throughput, like a robot assay here for drug discovery, or some algorithm-based cycle to improve or design the next experiments, or this is a kind of a robot. And the recent paper is kind of this type of robotic chemist. This is mobile, so it's move by itself and do some experiments. And this paper says 100 times longer if this machine tests solved by any human power. Anyway, this kind of a technology is coming, so probably the chemistry gradually, the way of doing chemistry is gradually changing. And also there is some review for how to use data science inside the chemical developments, and also some sort of automated the entire process, and something called self-driving laboratory or something. So inside a measurement machines, probably the result is more reproducible, and if we control this in very principled way, probably it's more efficient than the human infusion in some cases. So some researchers are expecting these kind of technologies, but still in inference. But there is a hot trend along this direction in chemistry. So this is the really purpose. So if you are interested in this kind of a trend, please see some of these kind of review papers. And actually, in production level, probably you will notice many things are robotized. So why not scientists also use robotics if you have money to implement this kind of a robot? But anyway, and also, for example, the company like Amazon is automated every transportation. So you click on the Amazon Prime order, then this kind of picking up robot is ship your order quickly. That is Amazon Prime works. So, and this is driven by the machine learning, of course. So very tightly related to machine learning technology in various aspects, just by analyzing chemical data set. So anyway, this is the last figure. This is by Jim Gray. So we need to unify chemical theory, chemical experiments, chemical simulation by some handling data appropriately. And this trend would be more strongly emphasized by machine learning or artificial intelligence or data science technologies. And this is our review paper, and chapter 2 is a very quick guide for machine learning beginners. And please check it if you're interested in the further topics. So this is the last slide. So thank you very much for all the time coming, and thank you very much.
So thank you very much, Takigawa Sensei. So are there any questions?
I have a question.
Oh, please.
Recent years, the machine learning or informatics techniques have a good relation with experiments, such as yes, as you mentioned, such as high throughput experiment or robot assisted experiment, and informatics techniques have also good relation with theoretical computation, but how can we use these three regions? I mean, theory and experiment and informatics. How do we mix them?
Ah, I see. That is, I think, one of the most interesting trend in the recent research. So actually, many research is ongoing, but the problem in machine learning is the most highest hurdle is we need the data. It's a good data, but for many problems, it's sometimes very difficult to get the large amount of data for a given problem. And in that cases, for various reasons, for example, it's I don't know, experiments takes financial cost or requires expensive devices or requires a very long time, something like that. Anyway, in that situation, probably computational results can complement the machine learning results. So mix up the computer simulation plus experimental observation plus machine learning or some statistical method probably complement each other's disadvantages. And this is a ongoing topic and no consensus for now, but also our research institute is trying to do something along this direction.
So there's no universal consensus for this. Okay, and we managed to mix them for each programs. Okay, thank you.
Questions?
I have a question about bimetals deep band prediction. I know the gradient. We can get the feature importance from gradient boosting method. Can we use something like guide as the guide for development of better combination of bimetals can we use the feature importance for development of better materials?
Yeah, I think so. But for that papers, it's a really artificial setup. Just to our interest is just to confirm machine learning can how accurate machine learning can predict the computational quantities. So that task itself has no real advantages. But if we set up more nicer descriptors or more controllable descriptors. So first of all, we cannot control the atom numbers or any. So we can not change the elementary features we use. So if we get the feature importance, we have nothing to do about that characteristics. But if we run machine learning about some controllable parameters, then we can get some insight on which parameters can be very influential onto the outcome. So that paper's task is very artificial and no practical implications personally, I think. But for more appropriately set up task with some controllable parameters, then we can do some more realistic chemistry, probably.
Okay, thank you.
So questions? So nothing? So finally, so thank you for joining in HSI 2020. So we were able to finish all the lectures. I hope these lectures will help you with your research. So thank you again. So let's finish.